Hello and welcome back to Homework Help for Math 2. Today we're looking at Unit 8, Circles, Angles, and Shapes, Lesson 1, Planning the Gazebo. In the Ready section, we are being asked to use the given measurement to find the measure of the missing two values, and we are told that we can leave pi in our answers. So, for number 1, we are given the radius, which is 1 meter, and we are being asked to find both the area and circumference of the circle. So, the area of a circle can be found by pi r squared, where pi is a constant. It's the ratio of a circle's circumference to its diameter, and it is approximately 3.14. If you're an engineer, it's approximately 3.1416, and r is the radius. So our direction said that we can keep pi in the answer, so we don't have to plug in for it. We do have to plug in for the radius. We're told that the radius was 1. Well, 1 squared is 1, and pi times 1 is just pi. So therefore, we're left with just pi. Now, this is area, and our radius was measured in meters, and area is a two-dimensional unit of measurement, and so our area is going to be pi meters squared. And that is our answer. If you plugged in for pi, you would get approximately 3.14 meters squared. Excuse me. But it is sufficient for us to leave our answers in terms of pi, so our final answer there is simply pi meters squared. Circumference. So our formula for circumference is 2 pi r. 2 is a constant, pi is a constant, r is our radius. So 2 is going to stay there. We can leave pi in, and our radius is 1. 2 times 1 is just 2, and so we're left with 2 pi. And again, we're talking about meters here, and circumference is a one-dimensional unit of measurement. So even though the circle itself is 2 dimensions, the circumference is a one-dimensional unit of measurement because it's the distance around the circle, and distance is 1 dimension, not 2. So therefore, our units here are going to be simply meters, and so that is our answer. If you did plug in for pi, you would get approximately 6.28 meters. Question 3. For question 3, we are given the circumference, and we are asked to find both the radius and the area. Well, going directly from circumference to area, it's not impossible, but it's definitely going to be easier if we get the radius first. So our plan here is we're going to use the circumference to sort of back into getting the radius, and then once we get the radius, we can plug in for the area just like we did with number 1. So again, the piece of information here that we're given is we're told that the circumference is 8 pi yards. Now, our formula for circumference doesn't change. So circumference, as always, is 2 pi r. It's also pi times diameter, but everything here is in terms of radius, so we'll use this version of our formula here. And I'm just going to plug in what I know. I'm going to go into the space for 4, but that's okay because we actually were not assigned to do 4. So our circumference is 8 pi. So I'm just plugging in for C, right? We were told that C was 8 pi, so I'm going to plug that in. And we can ignore the yards until we give our final answer. That's just our unit. But for right now, our circumference is 8 pi equals the 2 drops down, the pi drops down, and the r drops down. The entire right-hand side just drops down. So what we have is we have 8 pi equals 2 pi r. I want to get r by itself, so in order to get r by itself, I'm going to divide everything by 2 pi, because by doing that, the on the right, the 2's go away and the pi's go away, and so I'm left with just r. Actually, I shouldn't cross them off because I have to deal with them on the left as well. But the 2's going to go away and the pi's going to go away, and so on the right-hand side, I get r equals. So now I just have to simplify the left. On the left, again, my pi's are going to cancel, so they're going to go away, and 8 divided by 2 is 4. So, getting back to number 3, the radius is 4, and we're talking about yards here, and radius is a length, and so it's one dimension, and so it's 4 yards. All right. Once we know the radius, for the area, we can plug it in just like we would, quote unquote, normally get the area. Formula for area is pi r squared. We're told that we can leave our answers in terms of pi, and our radius is 4, and that gets squared. 4 squared is 16, and it's kind of a mathematical convention to if you have a value that has both a rational number and pi in it, you normally want to start with the rational number. So 4 squared is 16. I'm going to move that to the left. So this becomes 16 pi. Now, area is a two-dimensional unit of measurement, and so that means our final answer here is going to be 16 square yards. All right. If you were to plug in for pi and then round to the nearest hundredth, you would get approximately 50 square yards. Okay. Question 6. For question 6, this time we are given the area, and we're being asked to find both the radius and circumference. And similar to question 3, our job is going to be easier if we get the radius first. So we're going to use the area to sort of back into getting the radius. And then once we get the radius, it's pretty straightforward. We're just going to plug it in and get our circumference. So again, our formula for area does not change. Area, I'll do this over here on the right, I guess. So area is pi r squared. We are told that our area is 81 pi. We can ignore the inches squared for a second. And the right-hand side just drops down. Not really much we can do yet. I want to get r by itself. And so I have to deal with the pi, I have to deal with the squared. We're going to deal with the pi first. So we're going to divide by pi. What's nice about this is that basically all of the pi's go away, and I'm left with just 81 equals r squared. In order to undo squaring, I want to find the square root. So we take the square root of r squared. That gives us r. And then whatever we do to the right-hand side, we have to do to the left. So we're taking the square root. We do not need to include a plus minus in this context because we know that we're talking about radius, which is a length, and it doesn't make any sense to have a negative length. So this is a situation where we do not need to include the plus minus because we know that r is positive. We do not need to account for the possibility that r was negative, and then when you square a negative, you get a positive, but we know r is positive. So we can forego the plus minus. We only want the positive square root of 81, and the square root of 81 is 9. Do it in black. So r is 9. So our radius for number 6 is 9, and the area was expressed in square inches. Radius is a one-dimensional unit of measurement, so it's just regular inches, not inches squared or square inches. So our radius is 9, and looking at the circumference, well, our formula for circumference doesn't change. It's still 2 pi r, or pi times diameter, same thing. So 2, we're allowed to keep pi, And our radius was, I already forgot, 9? Yep, 9. So we plug in a 9. Everything is being multiplied, so 2 times pi times r. Multiplication is commutative, so the order doesn't matter, which means we can just do the 2 times 9, and we can sort of skip over the pi. 2 times 9 is 18. We can leave pi in our answer. Circumference is a one-dimensional unit of measurement. We're talking about inches, and so we can just say inches, and our final answer is 18 pi inches. If you were to plug in for pi, you would get approximately 56.52 inches. And not necessary to plug in for pi, but if you did, you would get approximately 56.52. Moving on to the set section. The directions here say, for each of the regular polygons below, find the measure of the interior angle, the perimeter, and the area. So we are told that we are dealing with regular polygons. And just as a reminder, with a regular polygon has all congruent sides and all congruent interior angles. There's a lot of symmetry with a regular polygon. As an example, a regular quadrilateral is known as a square because a square has 4 congruent sides and 4 congruent interior angles. There's no squares in this section, but again, if you're talking about quadrilaterals, a regular polygon is a square. And for each of these questions, we're being asked to find 3 things. The measure of an interior angle, the perimeter, and the area. Now, I guess in the interest of full disclosure, we're recording this video before we've actually had a chance to teach this lesson, and skimming through the lesson, it's possible that this type of problem was covered a little bit differently in class. I guess we'll sort of find out once we get to that point. So it's actually possible that we're going to be talking about these problems in a different way than what was discussed in class. And if so, either we'll modify the videos or we'll figure it out, I guess, when we get to that. But I'm going to go over these problems in a way that I think is easiest to understand, and I guess people can let me know how accurate that is. So for 7a, we have a 6-sided figure here. 6-sided figure is known as a hexagon, and because this is a regular polygon, we know that all 6 sides are congruent to each other. So we're told that one side length is 8. And so really what that means is every side length is 8. That's what it means to be a regular polygon. Additionally, with a regular polygon, all of our interior angles are congruent. So a 6-sided figure has 6 angles, 6 interior angles, and all 6 of them are the same measure. Now, for part A, the measure of one interior angle. The way that I would go about this problem, which again may or may not be the way that was discussed in class, but the way that I would go about this problem is I think that there's value in understanding how to divide up this figure into a series of triangles. And what I mean by that is if you just pick a vertex and you just start dividing this thing up into triangles like this, you'll notice that with a 6-sided figure, we have 1, 2, 3, 4 triangles. Okay, and that will be true actually for any 6-sided polygon. Any hexagon can be divided up into 4 triangles. And there's lots of different ways of doing this, but no matter how you do it, you should get 4. So with a 6-sided figure, we have 4 triangles, and each of these triangles, the interior angles sums to 180. So we have 180, 180, 180, and 180. So what that means is the total number of angles is going to be 180 the sum of all of our interior angles is going to be 180 times 4, because a six-sided polygon can be divided up into 4 triangles. So if we add up all of our interior angles, we get 720. All right. Now, I'm going to erase all of the red for a second. I'll just erase everything. We know it's a regular polygon. We don't need all those additional symbols. So the total, we'll say sub theta here. Theta represents our angle. So our total is going to be 720 degrees. We have 6 angles, which means if I want the measure of one angle, again, I'll use theta to represent that. Theta is going to be our total divided by 6, because every single angle is congruent, which means we're going to take our total and just divide by the number of angles, and we end up getting 120. So the measure of one of our interior angles is going to be 120 degrees. Okay. Perimeter. Now the perimeter is the distance around the figure. Well, we know that one side length is 8, and we know that all 6 side lengths are the same thing. And so our perimeter is going to be the 8 inches that comprises one of our 6 sides, and then just simply multiplied by 6, because they're all 8. 8, 8, 8, 8, 8, 8. So 8 times 6 is 48. Perimeter is a one-dimensional unit of measurement, and the 8 is expressed in inches, and so our perimeter is simply 48 inches. All right. Now for the area. The area is a little bit trickier. I'm going to erase this just in case we need the space here. The area is a little bit trickier, and again, the way that I'm going to look at the area may or may not be the way that it was covered in class. When I think of the area of a regular polygon, I always think of it in terms of, again, dividing it up into triangles, except that we're going to do it in kind of a different way, in that we're going to sort of start at the center and just go out to every single vertex. So notice that this is not 4 triangles. This actually turns out to be 6 triangles, but that's because we're sort of doing this in a different way. We're not going... we're overlapping, if you will. So our lines going from vertex to vertex, they intersect all at the center. Whereas with 7a, our lines did not intersect. That's why we only got 4 triangles the first time. But this is a different kind of problem, so we're going a different kind of method. And so every regular polygon can be divided in this fashion. And what's nice about this approach is that all 6 triangles here are congruent. They are identical triangles, which means if I want the area of the regular polygon, all I need to do is I need to find the area of one of these triangles, then simply multiply by 6, and that will give me the area of the hexagon. Okay? So now our goal essentially is to find just the area of one of our triangles, and then we're basically done the problem because we take our answer, multiply by 6, and we're done. So let's take a look at one of these triangles. I'm going to redraw it. I'll redraw it over here, and we'll just sort of have a lot of space to sort of work with. So I've taken one of the 6 triangles, and I've sort of separated it out over here. We are told that our base is 8. Right? And again, we're looking for the area of a triangle here, and the area of a triangle can be written as 1/2 base times height. And we're off to a promising start here because 1/2 is a constant. We know what that is. And our base, well, by telling us that the side length is 8, they're actually giving us the base, right? This is our base. That's great. So all we need now is the height. We need h. And if we knew h, we're practically done this problem, right? We solve for h. That gives us the area of one triangle. We multiply by 6. That's the area of the hexagon, and we're done with number 7. So all we need is h. In order to use h, we are going to have to use some trigonometry. And specifically, notice that for 7a, we found that the measure of one interior angle, which I'm going to go back to the original hexagon, so that angle in red is 120 degrees. All right, that's what we found in part A. And it turns out that the line that we drew through that angle, I'll do this in green. This angle that line bisects that angle, cuts it right in half, which means this piece here is 60, and this piece here is 60. So if we compare that to our picture on the right, we've taken one of our triangles and we've separated it out, and it means that this angle right here is 60. It also means that this angle is 60, but we only need to label it once. We don't need to label like every single thing here. Also in our picture, we're told that the base is 8, and we need to solve for this height. The height cuts our base in half as well. So when we drew our height, we took this oblique triangle. It's a non-right triangle, and by drawing the height, we turned it into two right triangles. And that base is cut in half, which means if our entire base is 8, it means that this piece is 4 and this piece is 4. And what's nice about this is that if I focus on just one of my right triangles, we're focused on the one on the left, right? So we can kind of ignore everything else. Notice that we have a right triangle. We have a right triangle, and we know the measure of one of our acute angles. In this case, we know 60, which also means we know the other one is 30. But we know one of our acute angles is 60, and we know one of our side lengths, and we want the other side length. Well, this is a prime example of where we want to use right triangle trig to solve for our other side length. So in terms of the 60, if I were to label this right triangle, my hypotenuse is over here, so that's capital H. The lowercase h, the height, this is opposite, and the 4 is adjacent. And I'm noticing that what we want is we want opposite, and we're given adjacent. And the trig function that connects what we want with what we know is tangent. Because the definition for tangent in a right triangle is opposite over adjacent. So what that tells us is that the tangent of 60 is my height of the triangle over 4. So height of the triangle over 4. And if I get h by itself, we get 4 tangent of 60. Now, depending on how comfortable you are with right triangle trig, the tangent of 60 is the square root of 3. And that gives us our height. Now, if you don't know the tangent of 60, you'd have to go and use your calculator here. But if you are pretty comfortable with right triangle trig and the unit circle, then the tangent of 60 is square root of 3. And I don't actually remember if we've gone over the unit circle yet or not. So we end up getting the tangent of 60 is root 3. Also, notice that we have, on the left here, we have a 30, 60, 90 triangle. And in a 30, 60, 90 triangle, if my short length is 4, then my longer leg is going to be that number times root 3. So because my shorter length is 4, it means that my longer length is going to be 4 times root 3. So I could also just get it just by looking at sort of the relationship in special right triangles. So my height is 4 root 3. So if I want my area, so we can now jump back to area, I know that it's going to be the area of one of my triangles. So the area of one of my triangles is going to be 1/2 times the base of the triangle, which we said is 8, times the height of the triangle, which is 4√3. Okay. And then we want 6 of them. So you could either start with the 6 or end with the 6. It doesn't really matter. So we take the area of one triangle, we multiply by the number of triangles, which was 6, and we get times 6. So if we want to simplify this a little bit, we can do 1/2 times 8 times 4 times 6. And you are more than welcome to plug that into your calculator. But if you do 1/2 times 8 times 4 times 6, we are left with 96, and we still have the √3 inches squared, because area is a square unit of measurement. Now, if you plug in for √3, if you take your calculator and plug this in, what we end up getting is approximately 166.28 inches squared. And so if you want to express your answer exactly, the area of this hexagon is exactly 96√3 square inches. And if you want to plug in for √3, which is an irrational number, it is approximately 166.28 square inches. Question 8. For question 8, again, we're talking about regular polygons here, and so that means that all of my side lengths are the same, which means every single side length here is 6. We're also told, or that also means that every single angle is congruent. So we have 5 congruent sides, 5 congruent angles. Any 5-sided polygon can be divided up into 3 triangles. And as we saw with 7, we're going to end up dividing this up into triangles that all meet at the center. But for what we're doing for A here, when you divide it up, you can't cross your lines, right? So that's why we end up getting only 3 triangles instead of 5 this time, because when we're sort of dividing it up this way, we can't cross our lines. We have to go from vertex to vertex, but we can't cross. So what that means is a 5-sided figure is, or can be, constructed using 3 triangles. So that means that the total of all of our interior angles is going to be 3 times 180. So that gives us a total of all 5 interior angles summing to 540. Okay? If we want the measure of just one angle, one interior angle, we're going to take that 540, and because they're all the same, we can just take our total and divide by 5. And that will give us the measure of one of our 5 angles. And so 540 divided by 5 is 108. So the measure of one interior angle is 108 degrees. The perimeter is very straightforward. The perimeter is simply the sum of our side lengths. It's the total distance around a figure. We have 5 sides, and every single side is 6, because that's included in the definition of a regular polygon. So 5 times 6 is 30. Perimeter is a one-dimensional unit of measurement, and so our total perimeter is simply centimeters. All right. Area. Erase this in case we need the space. And we'll get rid of all the extra stuff here. With area of a regular polygon, I tend to think of it as just taking my regular polygon and dividing it up into a whole bunch of congruent triangles. So unlike part A, This time, when we're dividing it up into triangles, you want to sort of start at the center and just go to every vertex. And so the number of triangles is going to equal the number of sides, which was not true for part A. But for part A, we were just doing something else. So we did A correctly, and now we're doing C correctly, even though we get a different number of triangles. So for area, we can see that we can take this. Oh, I forgot to use some vocab here. So this is a five-sided figure, and a five-sided figure is known as a pentagon. Pentagon, yeah. So we have a pentagon. It's been divided up into 5 triangles. And I'm going to redraw one of my triangles over here just to have a bit more space to work with. And again, I know that the area of a triangle is 1/2 base times height. And again, what's nice with this problem is that we're told that the base of the triangle is 6. And because I know that the area of this pentagon is going to be the area of one of these triangles times 5, the only thing I'm really missing right now is my height. If I could get this height, we are practically done this problem. So solve for h, and then we plug in and we're basically done. Couple things. That height that I just drew, that will always bisect the base, which means if my base is 6, it means that this piece is 3 and this piece is 3. Okay. It also turns out, just like we saw with 7, that we also know the measure of this angle, one of our base angles. And the reason that we know that is from part A, we found that the measure of one of the interior angles of the pentagon, before we divided it up, was 108. And when we drew the line here to create our triangle, that line also bisects the angle. It cuts it right in half, which means if we go over to the triangle on the right here, let me move this up. That's not what I want to do. Let me move this 3. I'm just going to move the 3 down here. Okay. So this angle that we've sort of indicated here at the base is going to be half of 108, which is 54. So that base angle of this isosceles triangle, it's isosceles because each of the lines that we originally drew in the pentagon, they're all congruent to each other. So what that means is that this is congruent to this. So this is an isosceles triangle. So the base angle is 54. And what we have here is we have a situation where we have a right triangle, and we know one of our side lengths. We want to find another side length, and we know the measure of one of our acute angles. And we could solve for the other acute angle. Turns out that it's 36, which means the entire thing at the top is 72. Our vertex angle is 72. And 72 plus 54 plus 54 is 180, which is a good little check there. And so anyway, in this situation, we can use right triangle trig to solve for our other side of this triangle. Now, unlike 7, with 8, this is not a, quote, special right triangle. The triangle in 7 was a 30, 60, 90 triangle, and so there was a sort of a ratio there that we could use. With 54 degrees, that's not a special right triangle. This is kind of a, quote, random triangle. So we really have to use our right triangle trig here. And so in order to solve for h, we're going to say, all right, well, if we're talking about the 54, then my hypotenuse is there. It's not really involved in the problem. Our height is opposite, and our 3 is adjacent. And the trig function that connects what we know, which is the 3, with what we want to know, which is the height, well, it's the trig function that connects opposite and adjacent. And the trig function that connects opposite and adjacent is tangent. And our angle here is 54 degrees. The definition for tangent in a right triangle is opposite over adjacent. Our opposite is the height, the thing that we're looking for, and our adjacent is 3. half of the base, which was 6. And if I solve this for h, we're going to multiply both sides by 3. So we end up getting h equals 3 tangent of 54. That is our height. That is our exact height. So now getting back to answering our original question, the area of the regular polygon. So we know that we can find the area of our regular polygon. We know it's going to be 5 triangles, 5 congruent triangles. So we're going to take the area of the triangle multiplied by 5. So it's 5 times, well, the area of a triangle is 1/2 times the base of the triangle is the same thing as the side length, the original side length, which is 6. And our height of the triangle is 3 tangent of 54. All right. So what we can do now is we can sort of plug in everything other than our trig function. So if we plug in 5 times 1/2 times 6 times 3, we will get 45. 45. And then tangent of 54. And we're talking about centimeters here, and so this is centimeters squared. So that is our exact answer for the area of this pentagon. It is 45 tangent of 54 degrees square centimeters. Now, that's kind of I mean, it's exact, but it's not like super useful. So this would probably be a good opportunity to plug in on the calculator. So 45 tangent 54. So we're going to do 45 tangent of 54, close parentheses. We need to make sure that we are in degree mode. So to make sure that we're in degree mode, we're going to press mode. And right here, we can see that our calculator was actually in radian mode. So I'm going to go down and over to degree and press enter. Now notice that degree is highlighted. Also, notice that at the top of the calculator, it now says degree. It used to say radian, but now it says degree. So if we press second mode to quit, and we've got our 45 tangent of 54, if we press enter, we end up getting 61.64. So going back to our answer here, so this is approximately 61.94 square centimeters. So if you want an exact answer, it's the one on the left, and if you want an approximate answer, it's the one on the right. Depends on the context. Sometimes you want exact, sometimes you want an approximate, but either one of those answers should be sufficient. Question 9. For question 9, we have another regular polygon. This polygon has 8 sides, which means it is an octagon. So the name of an 8-sided figure is octagon. This is probably the real-world example that most people think of in this case would either be a stop sign or the UFC fighting ring, which is literally called the octagon, and this is why. So this is a regular polygon, so all of our sides are the same, and all of our angles are the same. And there's a lot of symmetry in this figure. We can answer A without even dealing with the 10 inches at all. So let's go ahead and let's just answer A, and then we'll deal with the 10 inches. So for A, we want the measure of one interior angle, and as we've now seen a couple times, if you want to figure out the total of all 8 of our interior angles, so we want to sum them all up, you can take any octagon, not just a regular octagon, but any octagon, you can divide it up into 6 triangles. 1, 2, 3, 4, 5, 6. Okay? Every single one of those triangles, the interior angles sum to 180. So what that means is if I want the total interior angles for the entire octagon, we have 6 triangles, And each triangle has a sum of 180 degrees for its interior angles. So the sum here, I actually didn't solve for it, but let's see, 180 times 2 is 360 times 3. Let me just do it on the calculator. So 6 times 180. So 6 times 1. So 6 times 180 is 1080. So the total, the sum of all of my interior angles is 1080. That's for all 8 angles. 9a is asking for the measure of one of them. So what that means is if I want the measure of one of my angles, I can take my total, and because all 8 are the same, I can simply divide by 8 because they're all the same number. So when I take 1080 and divide by 8, I get 135. So what that means is the measure of one interior angle is 135 degrees. I'll go ahead and erase all this just in case we need to mess around with it. All right. So B is asking for the perimeter. Now, unlike 7 and 8, with 9, we were not given the side length. All right, we were given something else. What we were given is this is what's known as the apothem. All right. So we are told that the apothem of this regular figure, and the apothem essentially goes from the center to the center of the polygon, and it goes to the center of one of your sides. And as you can see, it forms a right angle. So that's called the apothem. So the apothem is 10. And what I'm going to do is I'll do a little picture. I'll do a picture here. We're not going to do 10, so I'm going to use some of the space for 10. So I'm getting ahead of myself. So if we take this octagon, and from the center, if we divide it up into a whole bunch of triangles, like this. Okay. Notice that the apothem, if I take a look at this triangle here on the right, so all 8 of those triangles are congruent, and the apothem actually turns out to be the height of one of my triangles. So if I go down here, and if I sort of redraw one of the 8 triangles that I just drew, the piece of information that we're given, which was the apothem of the octagon, it is also the height of my triangle, which is 10. Right? So I know that that's 10. And really, in order to finish out this problem, I need to know what is the base of my triangle. Because once I know the base, the rest of this problem, the perimeter and the area, becomes relatively easy. But I need that base. Notice that for part A, we were told that the measure of one interior angles was 135 degrees. And that is this angle right here, 135. And the line that we drew bisects that angle. So what that means is one of our angles in the triangle is going to be half of 135. Half of 135 is 67.5 degrees. So that base angle for this isosceles triangle, it's isosceles because those are the same, is 67.5. And what I'm looking for is I'm looking for this piece right here, right? Because I know that that is x and that's x, which means this is really 2x. So if I can solve for x in this picture, we're in a pretty good spot. And so we can use right triangle trig. And if we're referring to 67.5, then 10 is our opposite, and x is our adjacent. And the trig function that connects opposite and adjacent, it connects what we know with what we want to know, is tangent. So the tangent of my angle, which is 67.5, in a right triangle, the definition of tangent is opposite over adjacent, and so this becomes 10 over x. If I want to solve this for x, we end up getting x equals 10 divided by tangent of 67.5 degrees. So that is the exact value of x. Now notice here that we want 2x. All right, well this isn't too bad. We just double it. So when you double this, you get 20 over tangent of 67.5. Right? So that is our base of our triangle, is 20 over tangent of 67.5 degrees. And that is also the side length of our octagon, right? Because we've now seen that a couple times. The base of this triangle is one of our side lengths. So if I want the perimeter, well, I have 8 sides, and every single side has a measurement of 20 divided by tangent of 67.5 degrees. So if I want an exact answer here, 8 times 20 is 100 and not 120, but 160 over tangent of 67.5. That's an exact answer for our perimeter. We are talking here about inches, and so we have that many inches. But you definitely might want to be in a position to get like a more usable answer here. So again, I'm going to go back to my calculator, and we're going to do 160 divided by tangent of 67.5, close parentheses. We're still in degree mode, which I can verify up here at the top of my calculator, and I press enter, and I end up getting 66.27. So the perimeter here is approximately 66.27 inches. And so we have both an exact answer as well as an approximation. For the area of the octagon, we know that when we divided up our area, we had 8 congruent triangles. Every single triangle in that picture above is the same thing. And we just found on the right, we found that the area of any triangle is going to be 1/2 times. We solve for the base, which is right here, right? That's the base of the triangle. And so that is 20 over tangent of 67.5 degrees. And the height of the triangle was basically given to us, which was 10. So if I sort of ignore the trig for a second and just sort of multiply everything else, so 8 times 1/2 times 20 times 10, what I end up getting here is 800 divided by tangent of 67.5, and because it's area, it's inches squared. Now, if we want that, I'm going to do this down here because I'm running out of space. If we want an exact answer, we can again just go ahead and plug it in. So 800 divided by tangent of 67.5, close parentheses. We end up getting 331.37. So this is approximately 331.37 square inches. And so our exact answer is up top, and our approximate answer is on the bottom. As always, we'll wrap things up in the Go section, and the directions here say, find the perimeter and area of each figure. Your answers will contain variables. So we'll start with number 13. With number 13, we have a quadrilateral, EFGH, and EFGH certainly looks like a rectangle. And if you looked at this problem and you just sort of like assumed it was a rectangle, you got a little lucky. Maybe not that lucky, but you got a little lucky because this is almost certainly a rectangle, but it is also worth explaining or knowing why this is a rectangle. The symbols here and here, they tell us two things. The arrows tell us that EH and FG are parallel to each other, so they will never intersect. And the fact that they have the same number of hash marks tells us that EH and FG are congruent. That means that they have the same length. When you have a quadrilateral that has one pair of opposite sides that are both parallel and congruent, that tells us that our quadrilateral is a parallelogram. Okay? So that alone is enough information for us to assume that this is a parallelogram. And actually, parallelograms and rectangles have the same formula for both area and perimeter, so we actually could stop there. But this right angle, together with what we've already talked about, tells us that this is a special kind of parallelogram called a rectangle. So, long story short, 13 is a rectangle, but it is not because it looks like a rectangle. It's because we have one pair of opposite sides that are both parallel and congruent, along with the right angle tells us that this is in fact a rectangle. So, for number 13, we want the perimeter and area. Let's start with perimeter. And I'll get rid of all my extra stuff here. So we know this is a rectangle, and one of the properties of rectangles is that opposite sides are congruent. So that means that the top is also 3x plus 2, because it's the same thing as the bottom. And we also know that the left is, I'm not going to write it vertically, x minus 5, because the right is x minus 5. Now the perimeter means we just add all of these things up. So 3x plus 2 plus x minus 5 plus 3x plus 2 plus x plus 5. And if you were to write out the sum as 4 separate things, that's fine, right? And that might even be easier. For me, I find that it's easier with a rectangle to think of it as two sides that are the same thing. So we have 3x plus 2, plus we have 2 that are also the same, which is x minus 5. And again, if you wrote this out as just, plus, 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 that's also fine, but I just find that it's easier to think of it this way. So we want to distribute. So 2 times 3x is, 2 times 3x is 6x, and 2 times 2 is 4. 2 times x is 2x, and 2 times negative 5 is minus 10. And if we combine like terms here, 6x plus 2x is 8x, and 4 minus 10 is 6. We are not given any units here, inches, yards, miles, feet, whatever, so that's about as much as we can write there. And we're still talking about perimeter. So our perimeter for this figure is 8x minus 6, and as you can see, our answer does in fact contain variables. Now for the area. The area of a rectangle, which is also the same as the area of a parallelogram, is base times height. Now, what's nice with a rectangle is that our base and our height are our side lengths. That is not true for a parallelogram, but with a rectangle, we can just take one of our side lengths. We can take our length, which we'll call 3x plus 2, and simply multiply by our height, which in this case is x minus 5. So we've encountered a situation where we have the product of two binomials. In order to simplify this, we want to use the distributive property, and specifically, we commonly know this as FOIL, F-O-I-L, first, outer, inner, last. So our first multiplication is 3x times x, which gives us 3x squared. Actually, you know what? I'll do that in the same color. Why not? So we'll do that in red. So that's going to be 3x squared. Then O, remember FOIL, so in O, we'll do 3x times negative 5. So 3 times negative 5 is minus 15. Then we have an x. Then I in FOIL is inner, and so inner is going to be 2 times x, so that's simply 2x. And finally, the L in FOIL is last, so it's going to be 2 times negative 5, and 2 times negative 5 is minus 10. So that is FOIL. And our last step here is to combine like terms. We only have the single x squared term, so nothing combines with that, so that stays the way it is. We do have two linear terms. We have two terms with just an x in them, so we have negative 15x plus 2x is minus 13x. And then we only have the single constant, so that has to kind of stay by itself. And again, we're not given any units of measurement here. It's just all sort of abstract. So that is our area for number 13. Okay, for number 16. All right. Number 16. So we have another quadrilateral here, and this is not a rectangle. So hopefully people recognize that this green figure is not a rectangle, because rectangles are not slanted like this. However, it is a parallelogram. And the reason that we know it's a parallelogram is, again, just like we saw with 13, notice that we have a pair of sides, so VW and UT, where they are both parallel and congruent. And when you have a quadrilateral that has one pair of opposite sides that are both parallel and congruent, that is enough to conclusively say that your quadrilateral is a parallelogram. So with 16, we're dealing with a parallelogram. And what we want is we want both our perimeter and our area. So we'll start with perimeter. Get rid of my little scratch work here. Now, just like with a rectangle, one of the properties of parallelograms is that opposite sides are congruent. So what that means is if the bottom is 3x minus 4, then the top is 3x minus 4, which we knew from our hash marks anyway. Excuse me. So both the top and the bottom are 3x minus 4. And then notice that UV is represented as 7x plus 4, right there. And what we're going to want is we're going to want TW, which is also 7x plus 4. So we're not going to use this 7x over here, right? We're going to sort of temporarily ignore that 7x because that 7x is not a side length. It's something else, but it is not the side length of one of our, it's not the length of one of the sides of this parallelogram. So we're not going to use it for the perimeter. So the perimeter of a parallelogram, we have two sides that are 3x minus 4, and we have two sides that are 7x plus 4. And now we just need to simplify this. So 2 times 3x is 6x, 2 times negative 4 is minus 8, 2 times 7x is 14x, and 2 times 4 is 8. So if we combine our linear terms, 6x plus 14x is 20x. Negative 8 plus 8 is 0, and we certainly don't need to say plus 0 at the end, so they just go away. And again, we're not given any other units of measurement here, so we'll just leave it as 20x, and that is the perimeter of this parallelogram. The other thing that we were asked to find is the area. Just like a rectangle, the area of a parallelogram is base times height. Right? So the general formula does not change between a rectangle and a parallelogram. So you just have to, but you do have to make sure that you're using the correct base and using the correct height. The key thing with the base and the height is that they have to form a right angle. Right? That is pretty foundational to when you're talking about base and height. They have to be perpendicular to each other. And so what that means is if we let our base be 3x minus 4, the height has to be perpendicular to it, which means the 7x plus 4 is not our height. All right? It is a side length, but if we treat the 3x minus 4 as our base, our height has to form a right angle with it. And you can probably see where we're going with this. The 7x is our height, not 7x plus 4. All right? Now, theoretically, we could also use the 7x plus 4 as our base, but then we don't know the height. So that's we don't have enough information to use the 7x plus 4 because we don't have anything that forms a right angle with the 7x plus 4, but we do have something that forms a right angle with the 3x minus 4. So that's what we're going to use. So we're going to do base times height. I'll start with the 7x. So we're going to have, that's our height of 7x times our base, which is 3x minus 4. To simplify, we're going to distribute. So 7x times 3x, well, 7 times 3 is 21, and x times x is x squared. And 7x times negative 4 is going to be negative. 7 times 4 is 28, and the x comes along. And so our area is 21x squared minus 28x. Question 17 says, label all of the segments or lines in circle P with the term that describes it. And here is our figure. This is basically a vocab question. There is no calculations whatsoever that we're going to do in this problem. No numbers. This is just, can you identify the different ways that lines and line segments sort of interact with a circle? So this is vocab. There's not a whole lot of explanation. If any of the terms that we're about to write are confusing, I would encourage you to check out the glossary in the back of your book. All 5 of the vocab words that we're going to discuss right now should appear in the glossary. So if any of these do not look familiar, take advantage of the resources that are available to you and look them up in the glossary to make sure that you understand what they are. In no particular order, we have at the bottom here, bottom left, we have a line segment that has endpoints on the circle. All right, so we have endpoints there. And actually, you know what? Let me use a different color because I'm going to be constantly switching back and forth. So we'll use red for all of our dots here. We'll go back to that. All right. So in the bottom left here, we have a line segment that has its endpoints on the circle. That is known as a chord. So any line segment that starts and ends on the circle is known as a chord. Now, notice that we have another chord here. Okay? So that line that goes right through the center of the circle, that is also a chord. All right? That's also a chord. However, it is a special chord in that it goes through the center. And when you have a chord that goes through the center, that is known as the diameter. So the diameter is a special chord that not only does it start and stop on the circle, but it also goes through the center. Now, we also have, starting at the center, going to the circle. That is known as the radius. And without too much difficulty, you should be able to figure out that the radius is half the diameter. Equivalently, the diameter is double the radius. So definitely a good thing to know. Now, the other 2 figures with the circle are not line segments, they're lines. So really there should be arrows here, I guess, although I guess we're just assuming that they're continuing on indefinitely. So at the top, sort of going horizontally, we have what looks like a chord, except it's not a line segment, it's a line. So it goes through the circle. It doesn't start and stop. It actually continues to go beyond the circle. That is known as a secant line. So a secant line goes straight through the circle, doesn't stop, but other than that, it's kind of like a chord. And then we have another line in the top right here. Notice that with this kind of slanted line here, it seems like it intersects the circle once, right? At this red dot that's already there. That line, it seems to just barely skim the circle, and then it keeps going. It also happens to intersect our radius, which there's some properties there that we could look into. But that line that intersects the circle once is known as a tangent line. And there's a bunch of properties of tangent lines and radii and all that kind of other stuff. But for now, it's just vocab. So we have chord, diameter, radius, secant line, and tangent line. Please make sure that you can identify and use all of those terms. And if any of those were confusing, check them out in the glossary, and you should be good to go. Question 18. 18 says, identify each type of angle in circle Q and label the intercepted arc. Again, this is kind of a vocab question. So if anything that we're going to talk about in 18, there's no calculations whatsoever. If anything that we're going to talk about in 18 is confusing, I would again encourage you to check out the glossary just to make sure that you can identify all of these things. So I see two angles in this picture. The first angle is sort of in the center. So what we have here is we have a radius. I don't want to use a thick line, so we'll do it in green. We have a radius, and we have another radius, and those two radii form an angle. So radius, radius, angle. And in that situation, this angle that's formed is called a central angle, which isn't too difficult to remember because it's at the center. So when you have an angle that's like at the center, that's formed by two radii, that is known as the central or a central angle. We also have an angle on the left that's not in the center. So now we have, we'll do this in purple, I guess. So now we have an angle that is formed by this chord and this chord. And that's my angle there. And it's unlike the central angle, this angle is touching the circle itself. Because the central angle is touching the center, but this angle in purple is touching the actual circle, and it's formed by two chords. And that angle, I'll do it on the outside here, that angle is called an inscribed angle. Not as easy to remember as central angle because, yeah, just not as easy. But it is called an inscribed angle. I guess I should be pointing to the actual angle itself, which is this guy, right? That's my angle. So those are the only two, well, actually, those are not the only two angles I see, but those are the only two that we care about. And then the only other thing was to label the intercepted arc. Notice with 18, both my inscribed angle and my central angle, they both intercept the circle there and there. Right? So for the central angle, my two radii intercept, and with the inscribed angle, my two chords intercept. And what that does is it intercepts this piece of the circle. Right? That is the, actually, you know what? I'll do it around just to make sure that we understand what we're talking about here. So this is the intercepted arc. Well, if my handwriting couldn't get any worse, it gets worse when I'm writing vertically. So there you have it. But that piece of the circle is called the intercepted arc. And just as a little sneak peek here, notice that the inscribed angle and the central angle happen to intercept the same intercepted arc, which is going to be important later on.